Hello, I hope you guys are all doing well. For the final two lectures of this course, we're going to talk about some really neat topics in cosmology, and at the same time, some of these topics can be a bit abstract. So if you have any question you want to ask, by all means, please reach out to me via email, and I will respond to any question you might have. So this famous quote by William Shakespeare, and then, of course, I need to find a really cool stage in a Google image search for a background, and this is what came up. Now, in cosmology, we are going to really be talking about the stage on which physics takes place. So, to begin this idea, in physics, a force could be thought of as a push or a pull. So, we all have a good intuitive notion for what a push or a pull is like. Now, on a microscopic scale, because we are all made of atoms and particles, we could ask, what is a push or a pull? So let's take two positive charges. We learned earlier this module that positive charges will repel. So what's really going on? I can't bring these two positive charges close enough to actually touch each other because their repulsion will be greater and greater and greater, and eventually become infinite if they actually touch. So somehow these two positive charges need to know of each other's existence without being able to physically touch each other. And the way this happens is that both of these particles are continually creating little other particles that carry the information about what they are. So we would say that these particles, these two positive charges, are creating force carriers. So it's like these two positive charges create another particle and they exchange these force carriers between each other. So the one charge will create a force carrier, the other charge will absorb it and see the force carrier. This charge on the right knows the force carrier was created by a positive charge, so this charge is repelled. Similarly, if I take a positive and a negative charge, these two charges will exchange force carriers with each other, and the negative charge absorbs a force carrier and is able to see, hey, that's a positive charge, I should be attracted to it. Now, this is not a pure, absolute, accurate way of describing what a force is on a microscopic scale, but for the context of this course, my goal is to give you a good feel, a good idea in the spirit of what's going on with physics. Now, in classical physics, there are four forces. Another way of saying that is there are four types of interactions. So there's the electromagnetic interaction, there's the gravitational interaction, and we are familiar with these. There's also the weak force and the strong force. The weak force and the strong force we never interact with in our day-to-day life. Due to certain properties of particle physics, the weak force and the strong force, they will exchange carrier particles with other particles that could see that force, but they never exchange a particle further than the distance of an atomic nucleus. So we never interact with the weak force and the strong force in our day-to-day life. The electromagnetic interaction we do interact with. Anytime I pick up a book or a coffee mug, what is actually happening is there are atoms in my hand, and the electrons in my hand are repelling the electrons in the coffee mug. And so as I lift my coffee mug, eventually the electrons in my hand will repel the coffee mug upward, and that's why my coffee mug rises when I lift it. And the gravitational interaction should probably behave similarly. Now, all of these interactions I described, we talked about them, but we didn't really. I want to point out that these interactions take place at some location in space, and they take place at some moment in time. So in a way, I could kind of think of space and time as a stage on which all of these interactions take place. So this stage is a four-dimensional stage. I have three directions that I can move in. Where is the location of this interaction? Left, right, up, down, and front, back. And also, what time does this interaction take place? Does it take place now, or does it take place 5 minutes from now? So the stage I could think of as a four-dimensional background on which all of these other physical interactions take place. So, what are we going to do with this? In physics, a force is a push or a pull, and this picture here is basically you could think of as the periodic table for particle physics. So if you took chemistry, you had the periodic table, a certain arrangement of atoms that follow certain patterns. The standard model of particle physics is very similar, and all particles that we know of are contained in this table. So up and down quarks combine to form protons and neutrons. Here's the electron. Here's a photon, a particle of light. And there are some other particles out there too that are less common. Many of these particles will decay very rapidly. Some of them could live forever. So when we have an interaction like we are showing over here, we have some positive charges. These positive charges are going to be the quarks or the leptons, and then the baryons or the leptons. And then this particle that they shoot between each other, these are the bosons. So the particles that exist and shoot are these quarks and leptons, and then the bosons are the guys that carry the force and carry the information about what that force is. So not every particle is able to see every other particle. The quarks all have an electric charge. So the quarks will emit a photon, and the quarks will then see the leptons that have an electric charge. These leptons over here, the neutrinos, the electron neutrino, muon neutrino, tau neutrino, these particles do not contain electric charge. So a quark could send a photon. Photon carries the information about what is your electric charge, but the photon cannot interact with the lepton. So there are a bunch of different interactions that all these particles can, some particles can see some of them while they can't see others, but every particle is able to interact gravitationally, and this makes gravity relatively unique. So the takeaway message from this slide is that every particle might be able to interact with every other particle through the electromagnetic interaction, through the weak interaction, through the strong interaction, or it might not. But every particle can interact with every other particle through the gravitational interaction. So we'll send gravity away for the moment. Now, in classical physics, as I was trying to say, there are 4 types of interactions. There's electromagnetic, gravity, strong, and weak. And in classical physics, these interactions could have some really neat physics going on, but all the physics going on is just taking place on a boring stage. So you could have some neat stuff going on, but the stage itself is dull. From the point of view of cosmology and general relativity, the stage is now going to be exciting and dynamic. So in general relativity and cosmology, there is no such thing as gravity. There are 3 types of interactions. There's the electromagnetic, the weak, and the strong interaction. But these 3 types of interactions take place on an exciting stage with dynamics and hydraulics and pyrotechnics and other fun stuff like that. So what we think of as the gravitational interaction is actually just the stage on which all the interactions take place, being this exciting dynamical object. So, bye. Albert Einstein was made famous for realizing this fact. So Einstein's equations are a way to say what we really think of as gravity is not really a push or a pull. Gravity is just the fact that we interact with things on a really interesting stage that has properties. So gravity is essentially just the curvature of the stage on which things happen. So there are the Einstein field equations. There's this term g mu nu that tells space-time how to curve. So space-time, the stage on which all these interactions take place, will be curved and dynamic. There is This term T mu nu, that describes the location of all the stuff in the universe, all the particles of light, all the gas, dust, planets. T mu nu contains the information about where stuff is and what it's doing. And this term PHY just determines how strong gravity is. Gravity is curvature of space-time. So instead of left, down, upright, front, back being a simple way to describe space-time, in addition to what time is it, you now have this other weird thing where left, down, front, right, front, back, and up, down are not the most convenient thing to use. And aside from a few simple cases, there really aren't any known solutions to these Einstein's equations. Now, again, you'll never need to solve this for this course. I'm just pointing out that you have a term that describes the curvature of the stage, and you have a term that describes where all the stuff is on that stage. And then you have a term that describes how strongly the stage is affected by that stuff. You could imagine maybe in an alternate universe, gravity is much, much weaker for whatever reason. Then that would mean you put some stuff on the stage, but it doesn't affect the stage as much. The stage doesn't curve as much. And as a result, then there is a smaller gravitational force that we see. So, John Wheeler famously said that space-time will tell matter how to move, matter tells space-time how to curve. So we have the curvature of the background on which everything is taking place, and as that background curves, then the matter is going to move. And when that matter moves to a new location, the background will curve a bit differently. And because the background curved a bit differently, the matter will move to a new location. And on and on and on, back and forth. So for the most part, if you have a lot of curvature in your space-time, that's like saying you have a lot of gravity. So if you are on a kind of dull stage that is not very interesting, you have a really weak gravity in your surroundings. But if you're on an exciting stage with lots of stuff going on, you're in a strong gravity regime, you're probably going to be near a black hole or a neutron star. For context, gravity near the Earth is really weak. If one way you could convince yourself as that is the Earth, the entire Earth, which is huge, is pulling down, and it takes just a small refrigerator magnet to overcome the entire gravitational attraction of the Earth. So I'm going to stop the video here, and I'm going to begin talking about what do I mean by curvature of surfaces in the next video.